Today we're going to talk about solids of revolution. This is another volume by cross sections. It's still the integral of area times thickness. So we're going to see a lot of similarities with volume by cross sections. But here what we're going to do is we're going to draw a function and we're going to rotate. We're going to rotate that function about either the x or the y axis. We're going to rotate a region that's trapped in between two curves around the x or the y axis or some line parallel to either one. And when you rotate something around, you get a cross section perpendicular to the axis that you rotated around. So that sounds a lot like what we were doing with volume by cross sections. But here, the cross section is either going to be a circle or it's going to be a circle with a hole in the middle of it, so we'll call it a washer. And the area of a cross section of a disk is the area of a circle. So if we have a disk, and we'll be doing some examples like this, we know that the area is pi r squared. Now, to find the area of a washer, however, it's the area of the big circle minus the area of the little circle. So maybe we'll say the area is equal to pi times the big radius squared minus pi times the little radius squared, which could also be written as pi, parentheses really important here, big R squared minus little r squared. So let's see what that actually looks like and what these cross sections look like. Now here we're going to rotate the region bounded by y equals x squared, y equals 4, and x equals 0 about the y-axis. And so what we're talking about here, y equals x squared, y equals 4, and the x-axis, we're just talking about what's in the first quadrant, okay? Just talking about this first quadrant thing here, and what we're going to do is we're going to rotate that thing around the y-axis. So when we do, it goes around and it comes back. And what we're going to get here, if we draw this three-dimensional figure on this two-dimensional board, we're going to get this kind of a cone-shaped thing. And we're wondering what that volume is. Well, okay. Now, since we rotated around the y-axis, we got to cut perpendicular to that axis of rotation. We got to cut right here. Well, remember, this thing went around like this, and right back to where it started. And when it did, what we're going to get is we're going to get this cross section to be a circle. I take that thing out and push it over, we're going to get ourselves a circle. Now, what's the radius of that circle? How far is it from here to here? Now, let's see, we're coming out from here to here, and I know that's some x measurement, but I just cut the y-axis. I need everything in terms of y. In this problem, I am told that this curvy function over here is y is equal to x squared. So what's x equal to? Because I need this thing in terms of y, and x would be the square root of y. And so I'm not going to express my radius as x. I'm going to say my radius is the square root of y. And just like we did for volume by cross sections, what I'm going to do is I'm going to say that the volume is equal to the integral of the area. In this case, that area is in terms of y, dy, from wherever the y's start to wherever the y's end. Well, in this case, the volume is equal to, let's see, this is a circle. So I'm going to say, and I'll pull my pi out front, pi r squared, pi square root of y squared. dy. And I got to go from where the y's start, which is right down here at 0, to where the y's end, which is right up here at y is 4. And so if I find this, if I now put this into my calculator after setting up my integral, I should get that the volume is equal to, I think it comes out to be 25.113, something like that. Check it out, see what you get. You know, press pause whenever you have to. And if that isn't what it comes out to be, then email me, let me know. All right, let's move on to example 8. Same region as example 7. Okay. So it's this y equals x squared, y equals 4, x equals 0. Now we're going to rotate around the x-axis. Well, if we do that, what we'd end up with is something like this. And remember that, I'm going to draw this real lightly. I don't want to draw it with each one. But remember, this is coming out into our room here and back into the board. And so, yeah, this is a three-dimensional object. It looks nice and flat here because we're drawing it on a two-dimensional board, but it's a three-dimensional object. So what I want to do now is I would like to slice this thing perpendicular to the axis of rotation. And we rotate it around the x, so I got to cut it like this. And sure enough, if we cut like that, we're going to have a hole in the middle of it, aren't we? And so what we're going to have here is we're going to have this big outer circle and this smaller inner circle. And we remember that the area of any washer is pi big radius squared minus little radius squared. So let's find the big radius. And big radius, little radius, doesn't matter. It always starts at the center of rotation, at the line that we started from, the line that we rotated around, and it always goes back to the original figure, the far part of the original figure. Always to the original. I wouldn't draw the long radius down here and try and figure out how long that is. It's always from the line we rotate around to the far end of the original, and in this case, that thing's 4. Now, what about the little radius? Little radius again, right here at the place we are rotating around, but it only goes this far. How long is that? Well, that's a y measurement. Along this curvy guy here, what is y equal to? Well, y is equal to x squared. I need everything in terms of x because my slice here, slice the x-axis. I need everything in terms of x. So I'm tempted to write y. I'm going to write x squared. All right, so my area is pi big radius squared minus little radius squared. So volume, pi integral. And if you want to write the pi in here, you may do that. But I'm going to leave it on the outside. It's a constant, it's a coefficient. If I want to call 4 squared 16, I can. If I want to say x squared squared is x to the 4th, I can do that. There's my area. I got to multiply that by the thickness. And I got to make sure that I start at the low end of the x's and go to the upper end of the x's. So where did the x's begin? Well, it looks like the x's began at 0. And if this is the line y equals 4, if y equals 4, what is x out here? Well, if y equals x squared, and y is 4, I think that x value has to be 2. So I think we're going to go from x is 0 to x is 2. And now it's calculator time. Put this into your calculator. Double check. I think that's what we're coming up with. Example 9, same region. But now we're going to rotate around x equals 2. There's the line x equals 2. So this isn't the x-axis, it's not the y-axis, it's a line parallel to one of those. So if I rotate this around x equals 2, again, we're going to rotate around here, and we're going to end up back where we started. This is going to end up looking like curtains in a window. Something like that. But remember, it's a three-dimensional figure, and I kind of missed when I did this. We're going to come up with there. It looks like that. A three-dimensional figure, and it's round. If we look down at it from the top, we'd see it was round because we rotated around that line. And we've got to cut perpendicular to the axis of rotation. So we cut right here. And I think where we see that if our choice is a disc or a washer, we're getting a washer here. We've got a bigger outer circle and a smaller inner circle. And to find out what the radius is, we got to start at the center of rotation here, this line x equals 2, and we got to draw back to the far side of the original. Back here. Now, how long is that? How long is that line? How far is it from x equals 2 back to x equals 0? Well, I think that's 2. And no matter where I would have sliced it, if I had sliced it up here, it's still going to be 2 units from here to here. Now think about something. Think about where we slice this. Is this going to be in terms of x's or in terms of y's? And I'm hoping that you're saying, well, I think that slice would have hit the y-axis. Everything's got to be in terms of y. 2 is a constant, and that's what that big radius is. This little radius has got to be in terms of y. Now the little radius starts at the center of rotation here, and it just goes this far. How far is that? Well, that's some x measurement, I guess. How far is it from x equals 2 back to, let's see, well, that was y equals x squared. So x must be the square root of y. This is the line x equals the square root of y. How far is it from 2 back to the square root of y? Well, if we think about this, you know, if we do, how far is it between places on a highway? If this is mile marker 72 and this is mile marker 32, how far is it? Well, you take the big number, you subtract the little number, and on a number line, the big number is always to the right of the little number. So take big minus little, and we'd say, well, that's 40. Well, in our problem up here, how big is this little black segment that we've drawn? Well, the big number is 2, because it's to the right of that curvy function. And then we have to subtract away the curvy function, which is the square root of y. So that's the little radius. And so that's what makes these problems when we're not rotating around the x-axis or the y-axis, makes those a little bit tougher, because what we write down for our radius, sometimes it's the big radius, sometimes it's the little radius, sometimes it's both, is a little different than what we're used to. So I think that the area of this washer is pi. Big radius squared minus little radius squared. And so our volume, pi. I'll call that 4. I'm not going to try to square that thing. The possibility to make a mistake there and therefore mess up my final calculation is too great. So I'm going to leave that one alone. I can square 2 all day. That's going to be fine. And now where do the y's begin? Everything's in terms of y, and I think the y's again started at 0, just like example 7, and they go all the way up to y is 4. So we put this into our calculator, and I think example 9 ends up to be 41.888-ish, something like that. Check it out. Make sure that your numbers agree with mine, and if not, well, one of us goofed up somewhere. Example 10. Y equals x squared, y equals x. Well, here's y equals x squared. And here is y equals x. And you can see that what we end up with is this skinny little sliver down here, the shape of a willow leaf. It's something that looks like that. And we're going to rotate that thing. We're going to rotate that thing around the x-axis. We get something that looks like that. And remember, this would be, again, some cone-shaped thing. We go all the way around three-dimensionally. We rotate it. We don't just reflect it. We rotate it. And we do get a three-dimensional object. And it's pretty hollow. Okay, not a lot of material there. And we got to cut perpendicular to the axis of rotation. So we cut like this. And you can see there's going to be a space in the middle. You can see that this is going to be a washer, which has a big radius and a little radius. So what's the big radius? How far is it from here? Y equals 0. Up here, where y equals x. Now this has to be in terms of x because we cut the x-axis. So what is big minus little? And I think we see the big radius. It varies, but it's going to be y is equal to x. This y measurement right here. Now what about the little radius? See if I can draw that in here. Little radius starts at the center of rotation. I should be in a different color here. Let me go yellow. Starts at the center and goes out to here. How far is that? How far is it from y equals 0 up to y equals, well, that curvy thing is x squared. Well, if I take big minus little, I get that the little radius is x squared. And you might think, well, wait a second, isn't x squared always bigger than x? Well, no. Not when the x's start at 0 and end up, well, where do these guys intersect? Where is x and x squared the same? I think we can see pretty easily that's going to be at 1. That's going to be the point x is 1 and y is 1. So as long as x's are between 0 and 1, no, x squared isn't bigger than x. The area of this washer, pi. Big R squared minus little r squared. So the volume, we've already determined that the x's started at 0 and go up to 1. And the big radius squared was x squared. The little radius, when we squared that, I think we're going to get x to the 4th. I'm confident enough that I'll carry that one out. The x. This isn't going to be much of a volume because that really is a pretty small region that we're rotating around. And I think in example 10, we get something in the 0.419 range. Example 11 is the same region. We're going to have, let's see, I think it was y equals x squared, y equals x. But we're going to rotate this around. Y equals 2. So let's see, what are we going to get when we rotate around y equals 2? This point down here is 2 units below. I got to go 2 units above. And let's see, this one's probably going to end up like right about here. I think we're going to end up having something that looks like this when we rotate it around. Remember, this is a three-dimensional figure. We took this point right here, and we rotated it around that line and brought it back to where we started. And so we're going to end up with this three-dimensional figure. It's like a bowl, but it's got a hole in the bottom of it. All right, well, let's see. When we slice this perpendicular, the axis of rotation, I got to slice perpendicular to that purple dashed line. Go like that. I got myself a really big washer. I'm not going to draw this to scale. I'm going to draw a really big washer, though, which has a big radius. And it's got a little radius. And we always draw, remember, we always start at the center of the rotation. We always go back to the original figure. Now, everything in this problem, if we had continued this slice, we would have hit the x-axis. Everything better be in terms of x's. So up here, I've got y is equal to 2. But what's this down here? This is y is equal to x squared. Now, what's the difference between those y values? And if I take this minus this, if I take big minus little, I get that the big radius is 2 minus x squared. And if I'm looking for the little radius, maybe I'll do this in black. Starting at the center of rotation, but only going this far. Again, the big is y equals 2, the little is y equals x. And what's the difference between those? Well, it would be the 2 minus the x is the little radius. So the area of that washer, pi, big radius, squared minus little radius, squared. Volume, pi. Big radius squared minus little radius squared dx. And in this problem, where did the x's start? I think the x's started at 0. Where did the x's end? That's 1. So coming up with those radiuses, well, that's quite a challenge. Always do big, y equals 2, minus little, depending on which one you're going to here. Always big minus little to find that radius. Now, if we put this into our calculator correctly, for example, number 11, I believe it is 1.675-ish. All right, we got 2 more examples. Region bounded by y equals e to the negative x. Oh boy. I know e to the 0 hits at 1. E to the negative x looks like this. X equals 0 looks like this. Y equals 0 looks like this. And x equals 1 looks like this. So I think you can see the region that we've got here. And we're going to rotate that thing around the x-axis. So if we do that, I think we would end up with something that looks like this. I think we got that figure right there. And again, we rotated this thing around the x-axis. It went out here and it came back. And we got this circular figure so that when we slice it, we're getting circles, but no space in the middle of this one. So we haven't seen one of these since one of the first examples. Looks like we're getting ourselves a disk here. And all we got to know is the one single radius here. How far is it from the center, the far edge of the original figure? Well, I want this in terms of x's because I sliced the x-axis, which means I want a y equals equation. I want y equals e to the negative x because that's in terms of x. Down here, I've got y equals 0. Well, how far is it from big, from up above, to the one that's down below, and that's e to the negative x. Big minus little. The area of that circle, pi, radius, squared. So volume, pi, radius, squared. dx, everything in terms of x, we cut the x-axis. Now in this problem right here, in this figure, where do the x's begin? Where do the x's end? I think they started at 0 and they ended at 1. So now it's calculator time. And I do believe we get 1.358. Final example, same region. Same region, same thing that looks like this. But we're going to rotate this guy around. Y equals 2 again. And when we do that, to draw it, we kind of draw the reflection of it. But realize that this thing, and I'll just draw this in yellow. But this thing got rotated around that line and back to where it started. And again, a big bowl, a big hole in the bottom of it. And when we slice perpendicular, the line that we rotated around, we got that. We got ourselves a big washer. Again, I'm not going to draw this to scale. I'll draw a good size. Oh, that's a nice looking circle. We got ourselves a big radius. We got ourselves a little radius, but I got to remember, it's the line y equals 2. Now, think. Everything needs to be in terms of, I hope you're thinking x, because we cut the x-axis when we made this slice. So the big radius starts at the center. Always go back to your original figure, which is down here. How far is that? No matter where we would have sliced it, that big radius starts at y equals 2 and ends up at y equals 0. The big radius is 2. Now what's the little radius? Starting at the center of rotation, again going back to the original figure, but to the near part of the original figure. How long is that thing? How far is it from y equals 2 down to y equals e to the negative x? Well, I got to take big, because that's up high, minus little, because this is down below it. Big things are always higher than little things. So little radius is 2 minus e to the negative x. Area, I, big R squared, minus little r squared. And if you want to write that, you can. If you want to just jump right into the volume equation and say pi. Big R squared was 4. I'm not trying it. I'm just going to say 2 minus e to the negative x, parenthesis, squared dx. And since everything's in terms of x, I think the left-hand side of the x's starts at 0. And the x's ended out here at 1. All right, nice job setting up the integral. And man, I can't even read my own writing here. I think I got 6.585. But put it into your calculator, check it out. All right, that is volume by disc and washer. You've got the assignment that's posted in Schoology. And you've also got a take-home quiz. And if you are taking a look at this on Tuesday, because you're home for the ACT that the juniors are taking today, realize there's a take-home quiz that also needs to be completed before you come to class on Thursday.